Hello friends, this is Priyanka. Today we are going to solve a problem on given mechanism. In this video we are going to study how to draw Coriolis component of acceleration from the velocity diagram. I will give you some important tips. Please watch this video till end. Now first I will read what is the given problem. A mechanism of crank and slotted lever quick return motion is shown in diagram. If the crank rotates counterclockwise at 120 rpm, determine for the configuration shown the velocity and acceleration of ram t. Also determine angular acceleration of slotted lever. Crank AB 150 mm, slotted arm OC 700 mm and link CD 200 mm. So this was the given question. We will first draw the space diagram with some suitable scale. I will refer here scale 1:half. Now if we observe the diagram here, the length of the fixed link OA is given and which is equal to 400 mm. So 400 mm, that means 40 cm, and as per the scale 1:half we have to take this distance as a 20 cm. Now from this point A we have to take 45-degree angle from this vertical line and we will draw here the length AB, that is equal to, here it is given 150 mm, that means 15 cm, but 15 divided by 2, that is 7.5 cm. So in this way this point B is also getting fixed. Now here it is given that the distance in between A and D. So D is the point at which there is the ram. So we have to draw one horizontal line which is passing through the point D and which is having the motion along that horizontal line. So from this point A, this distance for this horizontal line is given, that is 300 mm, that is 30 cm. 30 divided by 2, we have to take here 15 cm distance and we will draw here one line in the form of dash and dot. Then it is given that the link OC. So link OC is given 700 mm, that is 70 cm. So as per this scale we have to take 35 cm distance and we have to draw link OC passing through the point B. So here is the link OC and then the distance CD is given 200 mm. That means as per the scale we have to take the distance in the compass 10 cm, take C as a center and mark here one arc. So point of intersection with this horizontal line will give us the point D. So at this point D there is the ram that we have to draw. And at the point B there is the slider that we have to draw, and the point B dash is the coincident point. So coincident point B dash I have drawn with the help of red marker. We will understand how this mechanism works and why the Coriolis component of acceleration is applicable for this mechanism. Now if we observe, the end point of this crank B is having slider and this slider is having motion along the link O to C. But this link O to C is having rotary motion about center O. So whenever there is the crank and this end point of the crank is attached with slider is having the reciprocating motion along any link and that link is having rotary motion, then this Coriolis component of acceleration is applicable. So the mechanism such as quick return motion mechanism, in that mechanism such a type of working is there. So we can apply here the Coriolis component of acceleration. Now what is happening here? The crank OA is moving in anti-clockwise direction. So at the same time here the point B is having attached with slider is having the reciprocating motion along this link OC. Link OC is having rotary motion about the center O and the point C attached to the ram D. and therefore this ramp is having reciprocating motion along this horizontal line. Now we will move for the calculation. So here the rotational speed of B with respect to A is given, that is 120 rpm. So from that we can calculate the angular velocity omega. So we know the formula 2 pi n by 60, that is 12.57 rad per second. Now from that omega we can calculate the linear velocity, that is V is equal to r omega. So omega we will take this value, and for this distance A to B we have to take. So this distance we have to consider in meter. So 150 millimeter, that means 0.15 meter, and if we calculate this we will get 1.9 meter per second. So this is about the magnitude. So what about the direction? So we know that the linear velocity is in the perpendicular direction to the link. So with the help of protractor we are going to draw one line perpendicular to the link AB. But in which direction we have to draw that line? So in the direction of motion. So motion is given in anti-clockwise direction. So if I align this edge AB with this protractor, so from the other edge we can draw here one perpendicular line. Now the direction is given, that is if we observe for this link AB, direction is in the downward. So here is also in the same direction, we will say this is the velocity of B. Now we will take some suitable scale and we will first draw the velocity diagram. Now we will move to draw the velocity diagram. As per this scale, 1 meter per second is equal to 10 centimeter. So for the velocity of B with respect to A is 1.9 meter per second. So scale is 1.9 multiplied by 10, that is equal to 19 centimeter. So first I will consider the fixed points. So in this diagram point A and point O are the fixed points. So consider here the point O, comma A. Now from this point I have to draw one line parallel to this VB. And what about this scale? So scale that we have to take, that is 19 centimeter. So here is the end point. So if I cross check, okay, so this end point is nothing but the point B. So this vector A to B indicates the velocity of B with respect to A. So simply I will say VB. Now if we observe from this point B, we can take one line, because here the slider is getting attached and this slider is having the reciprocating motion along this link OC. So how to transfer this reciprocating motion to the velocity diagram? So we have to draw one line parallel to the link OC but passing through this point B. So here will be small b, because in the velocity diagram we will use the small letters. So for this reciprocating motion I will use the red marker. So the motion of slider I will transfer, that is the line parallel to OC but passing through this point B. So exact direction is not known. So on both sides we will draw here one line. Now where is the exact location of the point B dash, because B dash is the coincident point and that is not known. So again if we move for the link OC, so how to show the linear velocity for this link? So we know that the linear velocity is in the perpendicular direction. So I will draw here one line that is in the perpendicular direction. So I will align one edge with this link OC and from the other edge in the form of dash draw one line. So this line is perpendicular to the link OC. So link OC, that means one point is O, that is the fixed point, and other point is C. So again I have to draw one line that is parallel to this construction line but passing through the point O. So take here this line. So transfer this motion. But where is the exact location of this point C, and that is unknown. So if we observe for this sliding motion passing through B and this link OC is intersecting at one point, one particular point. Now if we observe on this link OC there is the coincident point B dash. So the point of intersection is nothing but B dash. So I will show here this coincident point with the help of red marker, that is B dash. So what this vector O to B dash indicates, that is the velocity of B dash with respect to O. Now on this link there is the point C. So how to find out that? Now if we observe, here is the space diagram, and in this diagram we will take the ratio of O B dash to B dash C. So we will measure this distance with the help of scale, because this distance is not directly given in the question. So if we measure this distance O to B dash, it is 25.5. So as per scale 1:2, we have to multiply here 25.5 multiplied by 2, that is equal to, I will say O to B dash is 51, divided by B dash C. So this distance is 9.5. So 9.5 multiplied by 2, that is equal to 19, which is equal to, now this distance O to B dash. So in velocity diagram also we have to measure this distance. So if I measure the distance O to B dash, it is 17.5 divided by B dash C. So this B dash C is unknown, so we have to find out that. So we can find out easily. So we will take here 17.5 multiplied by 19 divided by 51, which is equal to 6.5. B dash C is equal to 6.5 centimeter. So we can easily plot this point, that is from B dash take a distance, that is 6.5. So here is the point, and this point is nothing but the point C. Now if we observe, point C is connected to point D for the link CD. So again we have to draw one perpendicular line for this link CD with the help of protractor. Now this is the perpendicular line. So I will transfer the line, that is the direction of line passing through this point C. Now in which direction? So direction is unknown. So I will draw on both sides of the line. Now at this point D, so here the exact location is unknown, but if we observe at this point D there is the ramp, and this ramp is having the motion along the horizontal line. Now we know that the reciprocating motion is always with respect to fixed points. So here is the fixed point, and we have to draw the horizontal line passing through the fixed point to indicate the motion of the ramp at point D. So I will draw here one horizontal line. Now this point of intersection is nothing but the point D. So if I draw this, O is a fixed point, O is the initial point, D is the final point. So this vector indicates the velocity of D with respect to O. So not necessary to write this O, because these are the fixed points. Now for this link CD, C is the initial point, D is the final point. So I will show arrow, so it indicates velocity of D with respect to C. Now here this line B to B dash is so much important. Now here we will take the initial point as a B dash and final point as a B. So velocity of B, so if I draw here the arrow in the downward direction, then it indicates the velocity of B with respect to B dash, that is VB dash, and then the arrow is in the downward direction. In space diagram we will show the direction of the velocity. So for this link OC, so if we observe, this is the link OC, and the direction that I will show here, C is the direction, and we can say velocity of C with respect to O. So O is the fixed point, so this link OC simply we can say VC. So here the direction is towards the left hand side, so I will show this direction and we will say VC. Then in the same way for this link CD, so here is the velocity of D with respect to C. It is having upward direction, so I will show here the vector, that is the velocity of D with respect to C, that is VDC. Now there is the question, that is the velocity of ram at D. So how to find out? So ram at D is having the reciprocating motion along the horizontal line, and this motion is with respect to the fixed point. So for that we have to measure this vector OD. So its length is 24 centimeter and our scale is 1 meter per second is equal to 10 centimeter. So 24 divided by 10, that is VD, is equal to 2.4 meter per second. So this is the answer of the question. Now we will move for the next, that is the Coriolis component of acceleration. Now how it is, the direction for this Coriolis component of acceleration is getting decided. So for that, if we observe, that is the slider at point B is having reciprocating motion. So we can say that with this coincident point B dash, this slider at point D is having linear velocity, and it is having motion along the link OC, and this OC is having rotary motion. So here for this rotary motion we have to find out the angular velocity, and for this reciprocating motion we have to find out the linear velocity. So now we will first find out here what is the linear velocity of this point B with respect to coincident point B dash. So from this velocity diagram we will find out here the distance between the vector B to B dash. So if we measure, we will get here 10 centimeter. So with this scale, that is 1 meter per second is equal to 10 centimeter. So we can say that which is equal to 1 meter per second. Now what about the direction? So direction is in the downward direction. So for the Coriolis component of acceleration, we will draw one line parallel to the link OC. So here is the link O to C, and here at point B there is the coincident point B dash. So I will show here with the help of red marker, and this velocity of VB dash is having direction in the downward direction. So I have to show this linear velocity direction, that is VB dash. Now we will move for the angular velocity omega. So omega for this link OC. So for this link OC we have to first find out the linear velocity from the velocity diagram. So we will measure the vector O to C. So vector O to C, that is equal to 24 centimeters. So as per scale it is 2.4 meter per second. So omega CO, that is this linear velocity divided by the length of the link. So length of the link in meter. So here VCO divided by CO, that is 2.4 divided by 0.7, because we have to take this length in meter. So which is equal to 3.42 rad per second. So this is the magnitude. So what about the direction? Now with the help of compass we will decide its direction. So we know that what is the direction of velocity is towards the left hand side. So O is the fixed point. So I will take here O as a center and move the compass in the direction of the velocity. So if I move the compass, then here is the direction, and this direction is the anti-clockwise direction. So I can say that this omega CO is having anti-clockwise direction about O. Anti-clockwise about O. Now we have to transfer this direction for this diagram, that is for the Coriolis component of acceleration. So there are we have to find out the direction of Coriolis component of acceleration from the direction of linear velocity as well as direction for the angular velocity for this omega CO. So here I will say this is the omega CO. So from this we can decide where is the direction of Coriolis component. Now if we observe here, when this linear velocity is having the downward direction and the angular velocity is in anti-clockwise direction, then we have to draw the Coriolis component of acceleration towards the right hand side. Now I have to draw this line perpendicular to the link OC. So with the help of protractor I will align one edge with this link OC, and from the other edge I have to draw one line passing through the point B. So here is the direction. So Coriolis component of acceleration, how to show? That is a raised to c. Now here a raised to c, we have to take the letter same as the velocity, that is b to b dash. That is the Coriolis component of acceleration of b with respect to b dash. I will give you important tip that how to decide the direction of Coriolis component of acceleration. Now here we know what is the direction of velocity for this b to b dash, and then we also know what is the direction of the angular velocity for the link OC. So now if we observe in this diagram, the direction is from point C towards point O, that is in the downward direction. So we will take here C as a center in the compass. Now the motion of the link is given in the anti-clockwise direction. So here if we take C as a center, and why we are taking C as a center? Because the velocity is from point C towards point O. That's why we are taking C as a center. Suppose this arrow is in inverse direction, that is in vertical direction, then we have to take O as a center. But in this case we will take C as a center, and the angular velocity is given in anti-clockwise direction. So if we take C as a center, and for the anti-clockwise direction I have to move the compass in this direction. So if I show this direction, here is the direction. So from left hand side towards right hand side I have to rotate the compass for this same anti-clockwise direction. So we can say that the direction from the left hand side towards right hand side. So in this way we have to draw this line for the Coriolis component of acceleration. Direction is towards the right hand side from this point B. So this is the hint, or we can say tip, to avoid the confusion. So for any direction of velocity and for any direction for this omega, you can apply this trick. Now we will calculate this magnitude of Coriolis component of acceleration. So what is the formula? So here is the formula, that is 2 omega multiplied by v. So omega for this link CO and velocity for this b to b dash. That is the velocity of b with respect to b dash. So if we put the value, that is 2 into 3.42 into 1, that is 6.84 meter per second square. Now we will move for the next. Now we will calculate the radial component of acceleration for the links, because we know the linear velocities from this velocity diagram. So radial component of acceleration for this link BA. So velocity of this link BA, that is 1.9. So we have to take its square, 1.9 square divided by length of the link. So length of the link in meter, that is 0.15, which is equal to 23.7 meter per second square. So the next link is DC. So for this link DC, again velocity, that is the linear velocity square divided by length. So here we have to measure this vector C to D. So its length is 5 cm. So as per this scale, for 5 cm we can say the velocity is 0.5 meter per second. So 0.5 square divided by length, that is 0.2. So which is equal to 1.25 meter per second square. Now we will move for the next, that is the radial component for this B dash to O. So this link B dash to O, we have to measure this vector O to B dash, and its length is 17 centimeters. So as per this scale we can say that the velocity is 1.7 meter per second. So 1.7 square divided by, what is the length? So we have measured already. So here the length is 0.51 meter. So which is equal to 5.6 meter per second square. So these are the values for the radial component of acceleration as well as Coriolis component of acceleration. And from these values we are going to draw the acceleration diagram. Now we will move for the acceleration diagram with scale 1 meter per second square is equal to 1 centimeter. So we will first draw the radial component of this crank AB. So this crank AB is rotating at the constant speed. So we will consider the tangential component of this crank is equal to 0. So what about the radial component? So we know that this radial component is parallel to the link AB and the direction is towards the fixed point, that is towards the point A. So if we show this direction, that is in the downward direction. So first we will select the 2 points, that is the fixed point as a O dash and A dash. Now from this point we will draw one line parallel to this AB, and with scale here radial component of AB is 23.7 meter per second square. That means we have to take the distance 23.7 centimeter and we will locate here the point B dash. So this point B is indicated as a B dash. Now if we observe this at this point B, there is the coincident point B dash, and which is having the Coriolis component of A, B, B dash. Now we will first understand this term. So if we refer the velocity diagram, so according to this direction of velocity, this Coriolis component of acceleration is getting decided. So if we observe here, the B dash is the initial point and B is the final point. And how we read this? The velocity of B with respect to B dash. In the same way, we have to write here the Coriolis component of acceleration of B with respect to B dash. That means here the initial point is B dash and final point is B. Now to avoid confusion, we will locate here the point B in the space diagram as a B dash in the acceleration diagram, and we will locate the point B dash in the space diagram as a point B double dash in the acceleration diagram. Now here the Coriolis component of acceleration for B to B dash is known as we have calculated 6.84 meter per second square. So we have to locate, or we can locate this with this scale and with this direction. But here we have to remember which is the initial point and which is the final point. So here the final point is B, that means B dash in the acceleration diagram, and initial point is B dash, that is unknown. So here I have to draw one line parallel to this Coriolis component of acceleration and direction in the same direction. But here the final point should be B dash. So I have to draw this line here. That is, I will take one line that is parallel to this Coriolis component of acceleration. I will take scale 6.84, that is approximately 6.8, and I will draw one line. So here is the point. So this point, that is, this is only one component. So I will say this point will be X. I will show the arrow in the same direction, and here I will say Coriolis component of acceleration B to B dash. So this Coriolis component of acceleration is perpendicular to the B to B dash. Now we will say the radial component of acceleration. So radial component of acceleration and this Coriolis component of acceleration are perpendicular to each other. So radial component of acceleration, I will draw here one line that is perpendicular to this Coriolis component of acceleration. Now the exact location of this point B dash is not known, that is, we will extend this line . Now we will move for the next. So if we observe here O dash is the fixed point. So from this O dash here O to B dash is the one link. So for this O to B dash, if we observe, we have calculated the radial component of acceleration. So we know that how we can decide this direction for this radial component of acceleration for this link O to B dash, that is in the direction towards the fixed point, and fixed point is the point O. So in the downward direction I have to draw one line, but parallel to this OB. Now here one point is O. So from this O dash I will draw one line parallel to link OB dash but in the downward direction, and with scale 5.6 centimeter. So here I will say, I will show arrow and it will indicate us the radial component of acceleration of B dash O. And here will be, I will say, point Y, because this is the component of acceleration. Now we know that this radial component and tangential component are perpendicular to each other. So we don't know the magnitude of tangential component. So here I will draw one line perpendicular to this radial component. And here is the point of intersection, and this point of intersection is nothing but the point B dash. So we will indicate it with B double dash. So here is the location of B double dash. Now if we join the end points, then we will get the total acceleration. So we can join here. So first I will say, I will indicate this. This will indicate us the tangential component. So tangential component of acceleration of B dash O, and this x to B dash indicates the radial component of acceleration from B to B dash. So now join the end points, that is this B dash to B double dash, and also this O dash to B double dash. Now we will move for the next. So this B dash is getting located. Now we know that the point C on the OB dash produced. So here we can say that, so total acceleration in between OB dash, that means O dash to B double dash. So I have to extend this link O to B double dash. And now we don't know where is the exact location of C. So for that I will take ratio, that is O to B dash in the space diagram divided by B dash to C, which is equal to here O dash to B double dash divided by B double dash to C. So here after calculation, B double dash to C is equal to 3.42 centimeter. So from that B double dash to C dash we have to take the distance 3.42 centimeters. So this point C dash is getting located. So if we observe the space diagram, here is the link CD. So again we will draw here the radial and tangential component of this link CD. So for the radial component of link CD, we have to take the line parallel to this CD and the direction is towards the point C. That is in this direction. So what is its value? So radial component is 1.25 meter per second square. That means we have to take the line which is equal to 1.25 centimeter, and here we will say the point Z. And then we will draw the one line perpendicular to the this link CD, but passing through Z, and it will indicate us the tangential component of link CD. So again we will draw here one perpendicular line. But where is the exact location of this point D? Now if we observe at this point D, there is the reciprocating motion along the horizontal line. So we will say that, or we will transfer this motion in the acceleration diagram as it is, that is the horizontal line but passing through the fixed point. So I will say, or I will draw here one line passing through this O dash and A dash, and this point of intersection is nothing but D dash. So in this way this diagram is getting completed. But here the total acceleration for this link CD, we have to join this point C dash and D dash. Now we will move for the calculation part. So here first question is that acceleration of ram at D. So this D is having linear motion along a horizontal line. So for the acceleration we have to measure the vector O dash to D dash, and its length is 8.7 centimeter. So as per the scale we will say that 8.7 meter per second square. Now the next question, angular acceleration of slotted lever. So here this slotted lever is O to B dash. So we will say that the angulation alpha for the B dash O. So how to find out that? So for that we have the formula for alpha, that is the tangential component of acceleration for this B dash O divided by length of this B dash O. So here what is the tangential component? So we have to measure the vector y to b double dash. So if we measure this vector y to b double dash, then its length is 7 centimeters. So here we have to write y to b double dash. Then its length is 7 centimeters. So we can say that as per scale 7 meter per second square divided by length b dash to O. So this b dash to O, we know this is 51 centimeter if we measure this scale. So we can say that as per the dimension we have to take in meter, that is 0.51 meter. So it is equal to 13.72 rad per second square, and this is the answer.